Okay, so sorry about the third video now. Flash to Chris, please. Yeah, shameful.
Who gave you that responsibility?
I'm sorry. She knew how to do a video. You did that. Okay, so this engine, or this water pump, is consuming 1.3 times 10 to the 6 joules of gasoline in an hour. So that means it's taking in this much heat, and that's what it's consuming. So that means that my heat in, my energy in, or my QH, remember they mean the same thing, is equal to 1.3 times 10 to the 6 joules. So right now we're just trying to figure out all of our pieces. We're still trying to say, this is my mass, this is what I have. I have also my energy that I'm putting in, so that's my QH. They gave us that. They also gave us a height. They're telling us that I have some height, or better yet, let's say a distance. We have some distance of 3 meters. So our problem here that we have is, in number 1, what's the thermal efficiency of the water pump? I know how to calculate thermal efficiency, and that is, I have to take the net work over the amount of heat that I put in. Well, we're given this bottom part. We're given the amount of heat. We're given the amount of heat that we put in. So we already know this one would be here. Okay, so we know this one, but we don't know the network. We have no idea what that network could be. But they gave us enough information that we can find work. One way that you can find work is by taking the pressure times the change in volume. Another way that you can find work is by taking the power equation. Power is equal to work over time. The way that you first learned how to find work was work is equal to, do we know? Do we know? What's another way to find work? Oh, she's funny.
I remember how to find it now. I don't remember how to
Joules.
Who just did that? 4 times displacement. Very good. Work is equal to 4 times displacement. They gave you a mass. You're lifting it up and down. So that means the acceleration due to gravity here for this force, or the acceleration must be the acceleration due to gravity. I have a mass. I know G. Did they give you a distance? They certainly did. So I can find my work by taking the mass, which is 7.6 times 10 to the third, by my acceleration due to gravity, which is 9.8, times my distance, which was 3 meters. If I multiply all of those together, you should get your work to equal 223,440 joules. So now you found your work. I'm going to put that over here to find my thermal efficiency. So the hardest part of this problem is that you have to realize they wanted you to find work by taking the force times the displacement. So that's the way you have to find work here. I consider this to be a hard problem because you had to realize that you needed to do this first, and you had to know that its acceleration would be the acceleration due to gravity. Once you find work, you can find your thermal efficiency. So if I divide those two numbers, we should get that our thermal efficiency is 0.172. But if we took that as a percent, we would get that to be 17.2%. And all this means is the water pump is only 17% efficient. It's really bad. Now we need to do part B. Okay, so again, all of this stuff for part A, and all we needed, the hard part about this was you had to know that you had to find work by taking force times displacement. Okay, so now we have part A. Let's do part B. And part B says, how much heat is wasted to the environment in 1 hour? I want to know how much heat is wasted or expelled or exhausted to the environment in 1 hour. So they're trying to ask you, what's the amount of heat that's leaving? You also know this to be QC. So what amount of heat is moving to the cold or lower temperature reservoir? I know my net work. I know my amount of heat that I'm putting in, and I know that's also related to the amount of heat that's wasted. So I can find my net work by taking the amount of heat that's absorbed minus the amount of heat that's released. We already calculated this from the first one. Remember in A, we found the net work to be this. 223,440 joules equals, they gave you how much heat is being taken in. And that's our QH. It's 1.3 times 10 to the 6 joules. And then my QC is just the amount of heat that I'm getting out. So if I just take this number and subtract it on both sides, I'd be left with a negative QC is equal to a negative this, but since they're both negatives, I can just erase that negative because it's a negative and a negative would just be a positive and a positive. So my heat that's given out, or that's expelled from this water pump, let me rewrite it, is a little bit more than 1,000,000 joules. So I'm only taking in this number of joules, about 1.3 million, and I'm releasing about 1 million. So it's actually not very efficient at all. We know that because it's only 17% efficient. So it should make sense to you that this number should be really large because it's not very efficient. So I know I'm losing a lot of my energy or a lot of my heat that I'm putting in. Okay, so again, let's go through part B again. How much heat is wasted to the environment in 1 hour? I know that what they're asking me for is to tell them how much heat am I losing. I know that heat lost and the amount of heat that's absorbed is how I would find my net work. We already found our net work. You were given your QH, or your amount of heat that's being absorbed. I need to find this one. So all we did was plug in the numbers that you were given or you found, and then you could find your heat expelled. Megan, will you go to the next slide for me, please?
I'll do.
Are you okay? I wouldn't know you.
Okay, so the next 3 slides, it's just doing the completely opposite thing. So a thermal pump is the opposite of a heat engine. A heat engine will take something from a high temperature, convert it into work, and then you get something left that's in a colder temperature. A thermal pump is the exact opposite. It will take energy from a cold reservoir, it will do an amount of work, and then it will expel it in a hot reservoir. This is how air conditioners work. This is also how your refrigerator works. It's exactly like it's the exact same process. You're taking something from a reservoir, you're converting it to work, you're expelling or exhausting some type of energy out. These are not 100% efficient. Can you go to the next slide for me, please? Okay, so this is just the opposite of what you've already seen in that first picture. I'm taking heat or energy from a low temperature, I'm converting it into some amount of work, and I'm also expelling heat into a higher temperature. So your air conditioner works because it's circulating or taking in air or heat or energy from the inside of your house, and it's releasing it to the hot outdoors, which is like 95 or 100 degrees outside. So you can think about it that way. And then this would just be an example, this picture to the other side would just be an example of following the process of the heat. Go to the next one. This would be a way that you can calculate the coefficient of performance. So it's the same thing as like the thermal efficiency as a heat engine, except we call it for a thermal pump the coefficient of performance. you need to be mostly aware of, the thermal, or the heat engine. You need to be aware of that E, that little funny epsilon, is equal to your network over the amount of heat that's absorbed. They're not so much going to test you on this one. So just be aware. On your homework, I don't think I gave you any problems with this. I only gave you heat engine problems. So we can just kind of glance over this or skip over this. Go to the next one. They will talk to you about a Carnot cycle. So this is called the Carnot cycle. It consists of 2 isotherms and 2 adiabats. They have to label your isotherms. They have to label your adiabats. They will always label them for you. Again, if I have this yellow shaded region would be considered what, Felicia? The amount of work that's done. Very good. Put you on the spot. So this yellow shaded region is the amount of work that's done by the engine. So we can see here are my isotherms, and they label these as your adiabats. They show this as a temperature entropy graph, but we could also very easily show it on a pressure volume graph. In the Carnot cycle, we say that a Carnot engine is the ideal engine. We want to think that maybe it could be 100% efficient, but we know that that's not true. So when they ask you to calculate the efficiency of an ideal engine, they're talking about a Carnot engine, or the Carnot cycle. Can you go to the next slide for me? We can find the ideal or perfect or maximum efficiency that a heat engine can have. When you're looking at this, and you're looking at your notes and you're writing your notes down, I want you to underline this. There's a difference in asking, what's the actual thermal efficiency? And then what the maximum efficiency can be. This is how you find the maximum efficiency.
You can't see that.
So this is how I would find the maximum.
You can't see it.
You can't see this?
You can't see the problem.
Like you can see this?
Yeah, because there's a glare on it.
If you back up a little bit, can you?
No.
You can like move horizontally.
Now.
Worse.
Dang it.
Move like left or right.
Okay, so Daniel says that you can't see this, so let me just rewrite it out for you. Okay, so this formula here, this formula right here, would be you calculating the maximum efficiency. So then what's the difference between calculating the maximum efficiency versus the actual thermal efficiency? Well, you know that your actual thermal efficiency is your net work over the amount of heat that you're taking in, or the amount of energy that you're trying to get in to the engine, versus maximum efficiency over here is still, you see your thermal efficiency one. It has the C there because it's trying to tell you that it's a Carnot engine. And Carnot engines just mean that it is an ideal engine that could get the maximum amount of work done with the amount of energy that you have put in. So maximum efficiency is this one, actual efficiency is this one. So we have done a problem with actual efficiency, that one is maximum efficiency. You have to make sure that you look for the word maximum. That's how they're going to distinguish between these two. Megan, will you go to my next one? Okay. So on this maximum efficiency problem, TC is going to stand for your temperature that you're getting from the cold reservoir, and the TH is going to stand from the temperature that you have in the high temperature reservoir. So this problem says an engineer is designing a cyclic heat